Alright guys, welcome to my next little video. Today we're going to be looking at periodic functions, okay? So here's one I prepared earlier, okay? So this is the basic function which we already know. So this is just the sine function, y equals sine x, okay? So quick recap of a couple things you guys know, okay? So I've drawn up a little table down here, okay, to just represent where we are at certain values. So what I mean by that is along our x-axis, okay, at 0 here, alright, the sine of x is also at 0. If we move across to pi on 2, we're all the way up here at 1. If we move across then to pi, we're back down at 0. We move across to 3 pi on 2, we're down to -1. And if we move across to 2 pi, we're back where we started at 0, okay? Now, you guys should already know that our period goes from here, from 0 to 2 pi, and that is how long our sine function takes to start, move up, move down, and then come back where we started from, okay? And from there, we know it will keep repeating forever, and also behind it will keep repeating forever. Our amplitude is the distance between the absolute top of our sine function and what's called the principal axis, okay? Now, for a normal sine function, that's actually just the x-axis, okay? So basically the principal axis is just the middle of our function, okay? At the moment it's easy, so it's just the x-axis, alright? So the middle of the absolute top and the absolute bottom matches up here at the x-axis, okay? So that's all well and good for just y equals sine x, okay? But there are other variations, okay? Similarly, we've seen before, for linear functions, okay, we don't just look at y equals x, which is the basic linear function. So this is the basic sine function. The basic linear function is y equals x. The way we cater for all the variations of that is we actually consider y equals mx plus c, okay, where the m represents the slope of our line and the c represents our vertical transformation, okay? So similarly, if we look at quadratics, okay, we don't just look at the basic y equals x squared. We actually take into account, well, there's y equals ax squared plus bx plus c, okay? And a, b, and c, similarly, they have their own little niches that they actually contribute to what it looks like. So they actually make a difference to what it looks like. So same for this, we're not always just going to get y equals sine x. We're going to get functions which involve a sine, but not just this basic one. And I'll plonk it down in this corner here, alright? The equivalent of y equals mx plus c or y equals ax squared plus bx plus c for a sine function actually looks like this. Okay, now on first glance, this looks a little bit more complex than for linear functions or quadratic functions, and that's true. Okay, but we're actually going to have a look at what. So there's an a, a b, a c, and a d, and we're going to have a look at what each of those individual things do. Okay, so let's consider them in isolation. So one at a time. So let's consider just what this a at the front might do. So let's start with what it would look like if we had y equals a sine x. We're going to compare the table which I did before, and I went through what each of those values mean. Okay, we're going to compare that with a new set that get changed. All right. So we're going to use an example, and we're going to use the example of 2 as a equals 2. Okay. So instead of just sine x in here, let's put 2 sine x. Okay. Now, at 0, 2 sine x will just be double what this is, so that'll just still be 0. At pi and 2, at all these points, alright, 2 sine x is just going to be double whatever sine x is, okay? So we're just going to double everything in this table, and we're going to have it all here for us, alright? So at pi and 2 it's 1, we'll double that, that's 2. At pi it's 0, double that, it's still 0. 3 pi and 2, double that, that's just going to be minus 2. And double 0 again, that's just going to be 0, okay? So, if we, on our graph, if we put in here, we've got 0, we put in 2 pi, pi, and then we'll go that for the middle ones. Alright, now we're actually going to go up to, as you can see, we're going to go up to 2 and down to -2. Alright, so if that's 1, that'll be 2. Okay, -1 and -2. Okay, so let's work our way across. Let's start from here at 0. Let's move our way up to 2, which is at pi on 2. Back down to 0 at pi. All the way down to -2. I'm going to go across my own graph here, but let's see how this works. And then back up to 0. Okay, so join in the dots. Okay, and so on that way. Okay, so comparing it to what we do over here, alright, the difference that this A makes, or that we change to 2, it actually changes our amplitude. Alright, so from here to here, okay, we're actually looking at a an amplitude of 2 now, instead of just 1 over here. Alright, the other stuff actually stays the same. Okay, so we're still hitting 0 at 0 pi and 2 pi. It's just that our, what would you call this, bell shape, alright, is just getting narrower and longer. Alright, and it would be the same if it was 3, 4, 5, alright, it would just keep getting taller and narrower. And it can become smaller as well. If our 2 was a half, alright, our curve would only go halfway up and then come down. Okay, so that's how we do it for A. Let's have a look for B. Okay, so guys, so for B, alright, if we isolate that, our function is going to look something like this. Okay, so y is equal to the sine of bx. Alright, now this one I've got rid of the table because I'm actually going to do this one in degrees because I think you'll see it easier that way. Okay, so let's consider normally, alright, if we look at just the sine of x, alright, we track our period by going from 0 all the way to 360. So from 0 all the way to 2 pi, that's 360 degrees. So let's track that like this. So it starts at 0, alright, gets to 90, gets to 180, 270, and finally gets to 360. Okay, if we just double that angle, okay, so by that I mean we use the example of, again, 2, y equals sine of 2x. Okay, that's why I said double. So if we just increase that angle or double that angle, alright, let's have a look at what happens. Well, 2x, if we just take what we have above it, well, that's still 0, goes along, but at here it's actually at 180. Keep going, and here it actually gets to 360. Alright, so what actually happens is all the numbers in between are all exactly the same, okay, but it just happens quicker. So from 0 to 180 it actually only takes from here to here, whereas over here it goes from there all the way across to here. So everything happens the same, it just happens half as quick, alright, or twice as quick really, sorry. So it still goes from 0 to 360, alright, but it actually just takes half the amount of time, alright. So our function here is still going to get from 0 to 2 pi, alright, or complete its whole period, but it's just going to do it quicker, exactly half as quick, which means, okay, if we draw it up, here's 2 pi, pi on 2, 3 pi on 2, okay, 1, -1, alright. Going up and down once again, that's all going to be the same, alright, it's just going to happen quicker, which means our period is actually going to happen like this. Okay, see how that, alright, we've actually squeezed the graph in like this. So we've grabbed that one and we've just squished it like this, alright. So now we go up, down, get back to our same spot, our period happens at half the speed. It only takes until pi. Over here, it takes all the way till 2 pi. Alright? And it will continue on like that. Okay? So you actually fit in 2 periods for the space of 1 that you do for normally. Okay? Now, we use the example of 2. If we use 3 or 4 or kept going high like that, it would just get narrower and narrower and narrower. Okay? And again, we can actually make it wider and wider and wider. If we made it sine equals a half x, it would actually be take twice as long to get to 2 pi. Okay, so our period would actually widen. Alright, so that's the variation that happens when we change the b value.